Conference, your source for JVM knowledge.
Yeah, I don't have anything else here. Close this. Amazing. So, as I said, I want to save your time, and I want to say a few words about for whom this talk. This talk is for mostly for reactive adopters. So if you are planning to use reactive programming in the future, or you are using reactive programming right now, this talk is for you. On the other hand, if you Spring developer and you are planning to migrate from, I don't know, Spring 4 or Spring Web MVC to Spring Web Flux, this talk also will be useful to you, because we are going to, at some point in time, you will notice that Flux is built on top of Project Reactor, and you have to learn reactive programming. And material that I'm going to cover today will be useful for you as well. And finally, this talk will be useful probably for everyone, because we are going to cover some internals, some multi-threading stuff, some concurrency patterns and techniques. And by attending this talk, you will be able to learn something about multi-threading in Java anyway. So if you're still with me, I'm going to shortly introduce myself. My name is Oleh. I'm from Ukraine, from Kiev. In Kiev isn't that sunny as in Madrid, so I'm happy to be there. And first of all, thank you for coming for this this talk and to this workshop. I work for Netify. At Netify, we are doing reactive stuff. We are building reactive protocol through the network. Also, I'm one of the contributors to Project Reactor. This is one of the tools we are going to look at today, and I'm trying to build my local community and support my local Java developers as well by organizing a big conference like DevOps UK and GECon. So if you are interested to visit Kiev, Ukraine, I'm welcoming you to visit those conferences, especially, and share your time between tourism and some knowledge learning or gaining. All right. Also, I'm author of this Reactive Programming in Spring 5 book. So if you're interested in getting some discount, or maybe if you will be super active during this talk, I will share some PDFs with you. This is basically it about marketing and me. And let's talk a little bit about today's agenda. So today we are basically start with understanding what is Reactive Streams Specification. Then, once we understood what is it, we're going to start implementing Publisher, which is part of the Reactive Streams Specification. After that, at the second part of our workshop deep dive, we're going to try to create something similar to Project Reactor or RxJava by our hands, and understand how it works and how it constructs and how all this functional magic works under the hood. Is it okay? Cool. Then let's move forward and start from Reactive Streams Specification. First of all, how many of you heard about this? Reactive Streams? Okay. So for those who haven't heard about that, I'll try to briefly explain what is that. Reactive Streams Specification is a document which introduces a few interfaces to reactive programming. The first one is a publisher. So the publisher is basically a producer of the data. It holds all the data that you might need to get from it. The second part is a subscriber. So it's obviously subscriber want to get some data to subscribe to it, to observe it. And the third part, once subscriber connected or subscribed to the publisher sends a subscription. So using subscription, publisher can say, hey, publisher, subscriber can say, hey, publisher, give me, for example, 5 elements. So subscription has this request n, or request, in this case, 5 elements method, which allows subscriber to say, give me an element, and publisher will be required to send less or 5 elements, but not more. So in that way, we get back pressure control. This is another part, like significant or essential part of reactive streams, which is called back pressure, or in that way controlling some flow of data. All the data is sent through the onNext method in the subscriber, and subscriber can react to them. So this is basically it. And from the first glance, especially if you look at the publisher interface, we will see just one method which accepts subscriber and allows in that way connect two parts. It doesn't look really hard. Who thinks this is something complex? No, it doesn't seem really complex. Let's try just for practice implement the array publisher. This is some version of publisher which takes an array as a parameter and sends this array to the subscriber. And one of the naive implementation could be something like that. We can just write a for loop and sends all the elements of array to our subscriber. Who thinks it will work? No one, right? It won't work. First of all, it won't work because specification, and specification has a lot of rules. It has almost 105,000 rules. I'm joking. It has only 41 rule. Let's take a look at those rules. There is some ruling for publisher. There is a lot of text. We won't read that. Let me enlarge it. We have some rule for subscribers. There is a lot of rules for subscribers, all 13, and we have some rules for subscription, and there is even more, 17 rules for subscription, which means that the implementation shouldn't be that simple as we saw before. In this workshop, we are not going to read all these rules. We are not going to understand why it was like that and why the authors of Reactive Streams Specification decided to do that in that way. But in order to simplify your understanding of Reactive Streams Specification and understanding how to implement the publisher, I'm going to focus you on the few first rules that required for building the first draft of the publisher. So the first rule, from my point of view, the most important one, is all methods on the subscriber should be executed in particular order. The first one should be executed on subscribe, and in that way, publisher should send a subscription to our subscriber. The second execution should be on next, and on next can happen from 0 time. For example, there is an empty publisher, so publisher doesn't have anything to send to its subscriber, so it won't invoke on. It might emit invoking on next method, as well as publisher can be an infinitive stream of data, so it can invoke infinite amount of time method on next. Finally, there is a terminal method, call it onError or onComplete, which allows to notify subscriber about some error or about completion of the stream. So I would like to pay your attention that we can handle only one of those, either only on error or only on complete, not both at the same time. This is important. Is that clear? Moving forward then. The second rule is about back pressure. If subscriber asked 5 elements, then producer or publisher should send only 5 elements and not more, or it can send less. For example, we have 3 elements in our array, but we shouldn't send more than subscriber asked for us before, from the publisher before. The next rule is, I don't know whether you know this guy. This is really controversial guy in Ukraine and in Russia area. His name Igor Bogayenko, maybe heard, but he say one good thing about programming in general. Null is nothing. It is something not good. And Reactive Streams developers and authors of the specification, they took care of us, and say that and prepared some rule that says that null is prohibited in Reactive Streams. We shouldn't send any null to our subscriber, and if that happens, we have to, for example, our array contains some null inside it, we have to notify our subscriber in some correct way, like through the on error signal and nothing else, in any different way. Finally, there is some two final tricky rules. The first one is about precaution, so we don't have to shoot yourself in the foot by calling on next request, on next request. We will see what could happen in case of such combination, but we should protect ourselves against this tricky case and this corner cases. And finally, if subscriber cancels, cancel, I don't want to receive any more data, publisher should eventually stop sending those data. Is it clear for now? Yeah, in case it's clear, then let's start doing the first coding session, and let's try to implement the first draft of the publisher. At this moment, you can open your, let me enlarge that as well. You can open your IDE, let it be even bigger. This it, or should I do it better, bigger? Okay, I think I have to make it a little bit bigger. Better. Okay, cool. So let's try it with analyzing what we have in our project. So we have plain Java project, we have build tool, we have Gradle as a build tool. In the Gradle we have a few dependencies, and the first one is dependency on Reactive Streams Specification. So this is the source where we can get all these interfaces about which I have been talking about just a minute ago. So we have here in our project this publisher interface. This publisher interface, where is that? Come on. Yeah, here we have this publisher interface. In case you are using Java 11 or at least Java higher than 9, you can access the same interfaces from the JDK itself. So there is a flow API which was introduced in Java 9 and provides us with the same set of interfaces, or simply copy-pasted interfaces into the JDK, which means that this specification and Reactive Streams is really important because they were ported into the JDK itself. And for this development, you can use either these interfaces or interfaces from the Reactive Streams lib itself. I'm going to use an interface from this lib. So this is basically it. The rest of the project is our array publisher and a test for it.
What branch are you on?
Yes, I am on the. Yeah, I have. I was asking you to check out this part 1 by steps commit branch, and you can look at the history of this branch, and you should be able to see this initial commit. So please check out this initial commit, and starts from that point.
Wait, where's the link to the repo?
Yeah, I guess you were a little bit late. Please maybe ask your colleagues about this link, and this link contains the link to the repo. Alright, so here is an identical publisher implementation we saw a couple of minutes ago on the slides. Identical. And in order to understand that our implementation is incorrect, we have to write some tests, right? Any objections? Other ideas? So we will be working in the kind of TDD fashion, and we will implement some first test, run it, understand that something went wrong, fix it, then implement another test, and so forth and so on until we implement our publisher. Is it fine for you? Okay. So let's start with the first test. In your guidance, you have those tests. Like there is, let me show you quickly. There is those steps, and each step contains some code snippet which you can copy paste to your project and try to run it. On the other hand, there is some solution hidden behind this section. So in case you are a little bit late and you don't had some time to implement the same code as me, you can open this cheat sheet and copy paste the implementation from here. But please don't do that. Let's be honest. And let's do everything by our hand. So let's switch to the test and let's implement the first test. And the first test was about calls ordering, right? So we have to verify that our implementation calls all the subscribers method in a particular order. So here I have a test. Let me quickly introduce what is going on there. So basically here we generate an array of long values. There is like an additional method there which allows me to quickly generate some random data within my, or not random, but data in range. It doesn't matter. Come on. Why you are so slow? And what is going on there? First of all, I create here my instance of array publisher and subscribe to it. I pass my plain uncomplicated implementation of subscriber, which on each call of every method put the information about this signal to some array, to some collection. So on subscribe means 0, on next means 1. On error, I don't expect that I got an error call, but I expect that I get on complete call. And finally, after all, I verify that all these signals are in place within my collection. So this is the simplest test that I can write. It collects all the signals into the collection and checks that all signals appeared in the right order. Is it clear? Cool. Then let's switch to our implementation. First of all, let's try to run this test. Let's do that. I don't know why he's syncing so slowly. Come on. Come on, buddy. Yay. Kernel task. let me quickly kill all this Java weirdness. Yeah, it might take so much CPU activity. Alright, as you can see, the first test didn't pass the verification, which means that we have to change something, right? Everyone got the same. Cool. So let's switch to our publisher and let's try to analyze what we can do about it. The simplest solution we can do, I guess, we can simply call any idea, first of all. How we can solve that? Wake up. Did you take some coffee before? Come on. Let's start thinking. Let's start communicating. So the first rule asking us about the order of the calls, which means that we have to call onSubscribe first and send some subscription. Then we have to call on next method a few times, and then we have to call on complete. So looking at this code and say what we can change here in order to satisfy required tests first of all. Okay, let me hint you first at the first time, and let me answer this question. The simplest we can do, we can call subscriber on subscribe here like this, and pass here an empty or anonymous subscription, right? We can do that. And then we can call on next method a few times, and then we can call on complete and rerun a test. So we are doing TDD coding, which means that we have to provide the simplest implementation ever. We don't have to implement everything in the correct way at the first time, but we have to satisfy what the test is asking from us. And in that way we can, as you can see, implement all required verification. Easy? Logical? Yeah, we can do that. Alright. Do the same quickly. And let's switch to the second verification. The second verification for today is about checking debug pressure, right? So we have, first of all, implement all this cool reactive stuff related to debug pressure, and in case our subscriber asked for n elements, we have to send n or less elements to it. So here I have this bug pressure support test. This is the second step in our guide. And this test checks the following. First of all, it generates the same array. It creates the same instance of the publisher, and in that case, it tries to externalize the subscription reference. And once we got the subscription through the onSubscribe method, just one attention from your side: please don't do that in production. This is kind of illegal or incorrect way to get access to subscription. But in order to verify in the rough way all this reactive stuff, I had to do that in this like this. And finally, what we do here, we collect all kind of data that we got from on next method or from our subscriber publisher, and then we manually call for first one element and expect that we receive one element. Then we call for another one element and expect that we got two elements in the collection. Then we call for two another elements and expect that at this point we have to have some 4 elements in the collection. Finally, request 20 elements and expect that we got all the collection filled. Is it clear? So let's try to run it. Let's try to run the whole test suite this time. And I guess as someone of you have already saw, we got a failure for this test, which says that we expected 0 element at this point at the first step when we haven't ever even request for any elements, but the collection was full at that point in time, which is absolutely incorrect. So let's switch back to our implementation and think what we can do about that. Any ideas? How we can fix this code?
So remove the for in the request.
Right. This is absolutely correct idea. And at the beginning I got some sweets for you. And please, this is the right answer. So this is the next motivation for you. Right, the simplest we can do about that, we can try to move this for loop inside request, because as you might notice, the whole interaction is in the subscription, right? We call subscription. So the simplest way to start sending data in the response to it is implement the same logic within request method, especially because within the request method we have this n value, which allows us to say, okay, we have to send only n elements. Then just let's say n elements. Okay, let's try to restart the test and see whether it was fixed or not. Of course it wasn't, because all the time we got first element or just one in our collection. Any idea why? Like we expected that at let me show you, at this point, at this checkpoint, like when we ask it for another one element, we should get 1 instead of 0. So the first element in our collection is 0, the second one should be 1, but we got 0. Is it clear what I'm saying about, what I'm talking about? How we can fix that? First of all, why we always send the same element to our subscriber. You definitely need some coffee. Any idea? Take a look at this.
Yeah, you're passing the same number now to the request.
I'm passing the same one element, but I always start from the 0 element because I don't have a state. So probably we have to implement some state, some index for current iteration. And yeah, the simplest we can do, we can create some index field. First of all, this field should be integer, because array couldn't be larger than integer or longer than integer. Index then integer, so we can create integer field, and we can iterate, we can increment this field this way. We can use it here, and instead of e we can no, this fine, and let's just try to run it and check whether it works or not. No, it doesn't work, and it doesn't work because we got array index out of bounds. Why? Because we don't have this verification that the index isn't higher than the length of the array. So let's simply put this additional verification, index less than array length, and finally we have to send on complete call, right? And we have to send this on complete call only when we got this index equal to array length. And let's try to run our test again. Cool, now it passes. Did you got the same result? So, again, to recap, a few things. We have to create an index field, which will be a state for current iteration. We have to increment this index along with the plain integer flag. And we have to use this index in order to get the proper arrays element and send it to our subscriber. Finally, once we done with that, like we got the proper value in the index, we have to check that at that point in time the index is equal to array length, which means there is nothing elements in the array, and we have to just say, okay, this is the end, complete. Is it clear? Cool. If it is, then let's move forward and let's implement the next rule, which is about verification for null elements. This is the simple test which gives me a null within my array, and our test should complete successfully without not successfully but with error. And once we got this error, we have to stop our iteration, and that's it, and check that we got this error after all. Cool. So let's try to run this test suite this time. And as we can see, the expectation wasn't matched. And it says that we expected the error, but we got on success, which means this is incorrect behavior for our publisher. So let's switch back and let's think what we can do about that. This should be simple this time.
We should implement an error.
Yeah, we probably should implement an error and check whether element is null or not. Cool. Please take another one.
Thank you.
Enjoy. So the simplest we can do here, we can do something like that. We can move this element outside and we can check, okay, element if okay, element, come on, it was working before. If element equal to null, then we have to say, okay, subscriber, an error, this is incorrect behavior. We have to send simple null points or exception, the same NPA exception, but through the normal channel, through an error channel. So subscriber will be able to get this exception and process it in the correct way. Finally, we have to exit our iteration, and now we can check whether it works or not. Yeah, it works. This simple fix provided a success for our test. Alright, let's move forward and let's move to, I guess, the most complex rule and implementation from the code perspective at that point in time so far. So the next verification that we have done, we have checked that we won't get into the recursion hell, and our publisher will work okay under this request on next circumstance. This is every time at the first step I got my subscription, I store it into the local state like as field, I requested for the first element, then I expect that I get this element, and once I got it, I have to request for another one in order to receive the whole collection. So this is a really common case in requesting data in Reactive Streams. In Reactive Streams. So this should be absolutely correct implementation of the subscriber. So let's check whether it works or not. Do you think? What do you think? Will it pass? No. Okay. It already failed. And as you can see, we got this Stack Overflow, which means something went wrong and we probably shoot ourselves in the foot. It shouldn't be like that. So let's switch back to our subscription and publisher, and let's start discussion again. Why it happened, first of all.
We are calling the next inside the request.
Right, yeah, and then calling the request produces another on next, and the next produces another request, and that for infinite amount of times. So any idea how we can fix that? How we can check that we are iterating right now? Maybe we need some flag for that? What do you think? No idea. Come on. Wake up. Can we use some additional flag here in order to check, for example, in order to check, like, am I iterating right now? Can we create some flag for that? Probably we can, right? We can. The simplest, of course, and the most straightforward will be implementing something like such field, like iterating is iterating. But I don't want to implement this way, because if we do something like that, let me quickly show you this implementation. If we create something like that, and if it's not iterating right now, so if it's iterating right now, we have to just return, like exit the request method. And if it's not iterating, we have to do something like that, right? We have to do something like that. We have to say true. And after all, of course, in order to say, okay, we exit iteration, so we can probably mark this field as false. This implementation could work, but with another fix. As you can see, each time we send an element, we request for n elements, right? And in this implementation, we don't have any way to understand whether how many elements were requested, right? Because if we recursively request for another element, we lose this n plus n number, right? So we have probably to store it somewhere. And we have, unfortunately, create another field, which is unfortunate. And the simplest solution is implementing and following some well-known pattern and well-known technique, call it work in progress verification. And we can implement this work in progress verification using this requested field. For example, we can do something like that. Instead of checking the Boolean variable, we can do something like, okay, let me use my code snippet. We can say, okay, let me read the initial requested number. Let me then increment this requested number to the specific value, and then let me check it. If initial requested is higher than 0, it means that someone iterating within this loop, right? So for example, someone requested before and started sending this data, which means that someone is working right now. And in case someone is working right now, I have to just simply increment my request size, and that's it. Because the previous guy who has been working by the time in this block will see this update and will just send a few other elements to my subscriber, right? After all we have to do, we have to decrement this requested size, requested number or requested parameter at the end, and we have to, okay, we have this E field which identify how many elements we have already sent. So we can probably simply move it here and put it here, and then decrement requested only once at the very end. Of course, we can rename this E to send, which makes our code a little bit more readable, and in that way provide the implementation for our test. So let me try to run it, because I can't forget it. I can't forget something because I'm human, and see whether it works or not. No, it doesn't. Why? Because I missed something, of course. And what I missed, I guess I know what I missed. Yeah, we have to do something like that. I always forget this part. So instead of M, we have now using requested in order to understand how many elements we have to send to our subscriber. Is it clear? Before we use this N, because we expected that we just got one call to request, and we send those number of elements without having this crazy request on next request or next corner case. But in that situation, we have to use requested, because requested can be changed at any point in time. So we have to follow this field in order to get the latest number of requested element. And now if we restart our test, we will see that it passes. Is it clear? Now let's quickly switch to the final. Let me quickly switch to the final rule, and let me check that in case we cancel our subscription, we won't get any more elements. This is the latest rule I mentioned in my slides for this first simplest implementation. So let's try to run our test use with this simple test. And as you can see, at the very beginning of my execution life cycle, I got my subscription. I say that this subscription should be cancelled. Then, just in order to test that nothing will be exploded, I request some N elements, and I expect that I won't get anything over on next, and I verify that after all I will get the empty collection. So this test doesn't pass at this point in time, so we have to fix that. Let's come on, what is going on? This is my computer. So do you have any idea how we can fix that? As you might remember, there is this cancel method, and it is empty right now. So come on, any idea how we can fix that? How we can prevent sending more elements in case of cancellation?
Request it to 0. Request it to 0.
How it help us? How it can help us?
It won't iterate the for. Request it to 0.
but someone can request after cancellation some data.
You can have a flag and ask for this flag when before the autocomplete.
Right. So another winner. The simplest solution here is, simply provide this Boolean flag, call it cancelled, and checking this flag all this time whether it cancelled or not, and implement the iteration with regard of it. Cancelled. If cancelled, just simply return. We don't have to send anymore. If cancelled, just simply return. We don't have to send incomplete if it's cancelled, right? So let's do that this way, and let's check whether it works right now or not. Yeah, it works. So this is the first win for us. We implemented the first simplest implementation of our publisher. But as you might remember, there is, let me show you, a lot of other rules, right? And we just implemented 5 tests. I don't think all those tests can satisfy and check all these crazy rules and all this crazy ruling. And I'm probably sure you are as lazy as me, because I don't like to write a lot of tests. I'm really lazy developer. Like, test is really important, but I don't like to write them. Again, I guess no one likes it. Maybe someone likes it? No one, right? Zeus, we don't want to implement all these rules. Fortunately, there is a solution. There is a built-in solution created and provided for us from Reactive Streams authors and from Reactive Streams Specification developer. And this is a collection of tests which can, let me show you, which can verify your publisher. Reactive Streams JVM provides this additional module called TCK, which translates as Test Compatibility Kit. And this Test Compatibility Kit allows you to verify your publisher, subscriber, and whatever you want without writing any additional tests. So let me quickly show you how we can start using this test suite. First of all, in order to start using this test suite, you have to have this additional link on Reactive Streams TCK in your project. You currently have it, so you don't have to put anything, but just for your information, this is under this link, this test suite under this link. And now, in order to start using it, the only thing you have to do, you have to extend your test from publisher verification. You have to specify that this is, for example, long publisher verification. And after all, you have to implement just a few required methods from this TCK. You have to provide a working version of your publisher, which asks on every test for some specific number of elements. So every time this method has been invoked, you have to generate some publisher with specified number of elements. And since our publisher should work fine, we don't expect any failure. We just ignore this failed case tests and return null, which is allowed for this test suite. So if you don't want to test any failure case, you can just simply return null in this case. And after this, you can restart your test suite and observe much more implemented out-of-the-box verifications for all possible rules, which is good. Do you see it? We have almost all past tests, and each test has some reference to a specific rule, and in that way you can understand what is going on. At the moment, at the current moment, we have only 2 failed tests related to some corner cases related to this crazy subscriber asked for -1 element. So our publisher should kind of check this corner case and should prevent this request, and should prevent it in the sending on error signal to our subscriber by saying, okay, you're a crazy guy, stop communicating with me. So we have to implement this logic, and the simplest we can do, we can just provide a if-else statement that checks that requested number of elements is higher than 0, right? Yeah, this is the simplest. So let's do that. Come on. It drives me crazy. So the simplest solution for that is provide something like this, if-else statement, and in case of n is less than 0, we can simply cancel our subscription at all and say, okay, we just canceled, so we can send an error message to our subscriber and avoid this additional messages after all. So in this way we can prevent this additional signals after the terminal signal. And if we run our test suite again, we will see that everything works fine and we got absolutely correct implementation, right? Yeah, so let's do, at that point in time, let's do some summary. I will stop for another minute here. In order to let you create a similar solution. And right after that, I'm going to return back to our presentation. Does anyone noticed, or did anyone notice that something about this picture? Is it correct picture? First of all, what do you think about that? Let me show you this reactive streams behavior again. So you should probably observe the difference. Got a subscription, and we start communicating with publisher. Is it true? Are we communicating with publisher? No, we don't do that. We communicate with subscription, right? So the correct picture should be something, not there. The correct picture should be something like that. And all the communication is done between subscriber and its subscription. And I would say that every publisher implementation is done in the similar way. So you don't do direct communication between publisher and subscriber. You do communication between your subscription and your subscriber. And all this communication is going in this way. So this is the first you have to remember about Reactive Streams. Everything is within subscription, and subscription in Reactive Streams is the central object, I would say. The next, what we have to remember, first of all, is work in progress pattern, which allows us to prevent this infinite recursion and prevent this shooting ourselves in the foot. The next part we have to remember when we implementing publisher, that there is a Reactive Streams TCK which provide us all required test suites for publisher verification. Finally, if we summarize this first step in our implementation, it just worked, right? It just worked. Tests are passing, which is good for us. A little bit complex because of this specific ruling of Reactive Streams, but everything clear and logical, right? Do you have any questions so far? Cool. Let's move forward. And unfortunately, this implementation isn't the final one. because we are living in the Java world, and this means that we are living in the multi-threading world. Have you ever had some experience with multi-threading? Yeah, cool. So let's refer to Reactive Streams Specification, and let's try to understand first of all what it says, what the specification says about multi-threading. First of all, the specification says that all execution should be done in the serialized way. So all the access to our subscriber should be kind of sequential or serialized, which means that only one thread at a point in time should have or should call all this method on the subscriber instance. Is it clear? Yeah. Yes, this should be simple. Then Reactive Streams Specification says that call to request method should be non-blocking. It says should be. It doesn't mandate us to provide non-blocking implementation, but it recommends us to create non-blocking implementation. And finally, it mandates us to create cancel in non-blocking way, because releasing of the resource should be a synchronous operation and should stall the requester from the resources. Finally, let's try to understand whether our implementation is multi-threaded or not. And in order to understand whether our implementation is multi-threaded or not, we have to provide an additional test for that. Let me add it. Test multi-threading. And in this test, I'm doing the following. I receive the subscription, and I'm starting calling the request one from the different threads. So in that way, I'm trying to check whether the implementation is able to handle some corner cases in data handling, in data requesting. So let's simply try to run this test and see whether it works or not. I guess it's clear. It won't work. Yeah, it won't. We requested for 5,000 of elements, and we only got a few of them. So let's return back at that point to our implementation, and let's start thinking how we can solve that problem. Any idea? Any multi-threading and concurrency experts here?
To synchronize something.
Yeah, the simplest we can do, we can write something like that. Let's just try it. I don't say that this is absolutely correct solution.
Synchronize, like not exactly synchronize, but to prevent them from running together.
Come on, what are you doing with me, computer? I guess the simplest we can ever not here, but here. Come on. The simplest we can ever do, we can write a synchronize keyword on our request method, and in that way prevent any concurrent access to this section. And let's just try to see whether it works or not. I guess. Right, yeah. It should be public. It passes, but it's not non-blocking implementation, right? Because in case we got some few simultaneous execution or call on the request method, we probably some of the thread will be blocked probably, right? So we have to avoid using this synchronize method, and we have to follow all the recommendations from the Reactive Streams Specification. So I guess the next simplest and naive way to try to solve it is using volatile keyword, Everyone aware what is volatile? So in a few words, volatile allows you to make your fields specified with or marked with this keyword available for all threads. So all threads will see changes in those fields. This is the simplest explanation of volatile. So let's try to run our test in this way. But do you have any opinion? Will the test be passed or not? Of course it won't, because volatile won't help us and won't save us from racing. And even the IDE says that non-atomic operation on volatile field appear in the code. So the field is volatile, but we have some non-volatile increment like that. Any other idea how we can improve that?
Atomic increment.
Right, we can use atomic fields. And we can replace all the volatiles with atomic operations and with atomic primitives. I'm going to simply use a code snippet here because I'm really lazy. And here I replaced all these volatile fields with atomic fields, which allows me out of the box apply this atomic increment and get and this atomic decrement and get, and avoid this concurrency problem. So any bets on whether it pass or not? Will it pass? Won't it pass? Just raise your hand. Okay, one hand that it won't pass. Let's try and let's see whether it pass or not. And it didn't pass the verification. At that point, I would like to switch back to my slides and explain this corner case using my slides instead of doing this on finger. So this is the code we just wrote in our IDE, and yeah, as I simplified general solution to a few lines of code where we read the initial requested size and we increment at the same time this requested field. Then we do that verification, and after all we get an access to this exclusive part of the code after verification if someone work in progress, if someone doing some work. And what can happen at this point in time? Just imagine that we, the black line or the highlighted code with black line is thread A, okay? This is thread 1. So currently the thread 1 is working in the code base. It incremented the requested field to the 5. It read that initial requested is equal to 0, which means that this thread can simply start doing work. So it passes and enter the element sending logic. And what can happen? At the same time, we can get a request from the thread red or from the thread B. And in that case, it can work fine until the moment when thread black finish its execution. So we can got a situation when one thread just entered the request method and another tries to exit it. And in happy case, the thread black will decrement the sent amount of elements, so the requested number will be 0. And since we have this atomic guarantees, which means that if we decremented this number first, then this happens before this execution, so the thread red should observe changes done by the thread black and should increment requested number to, for example, 5 and read this initial requested to 0 and start doing his work. This is a fine case. This is a happy path. But what if the thread black or thread A is really slow? He's loser, and thread red or thread B is winner and really fast, and the relation between this increment and decrement will be win by the red thread, and the red thread will increment requested number to 10 and read that, okay, initial requested is 5, which means that someone working right now, so I have to just simply exit, and at the same time this loser will decrement requested number to 5, so decrement the sent number and exit, and the red exit, and we got something unexpected because both threads have exited execution and no one will ever send new elements. This is a real problem. So let's back to our solution and let's try to think about it. Any idea how we can solve it? So let me give you some hint first. We saw that situation when one thread entered this code and another exited, and basically what we need to do is doing something. Okay, you saw that add and get returns some value. It returns the current state, right? So let's just put it in the current state. What will be ideal in our case if we do something if current state isn't equal to 0, so we just decrement our field and observe that we got another portion of requested data. So if current state is higher than 0, we have to just repeat execution, right? So we have to repeat this logic again. How we can do that? How we repeat something? Come on.
Either way.
Right. Another bonus. We can write a while loop, right? We can basically write something like that. We can write while true, just do the work and that's it. And don't ask anything, just do the work. And stop doing the work only in case if current state is equal to 0. So just simply return execution. And if the state isn't equal to 0, just reset send and start doing your work again. That's it. And this simple fix should fix the test as well to green. And it passes, which is amazing. All right, let's just run the whole test suite in order to make sure that we didn't break anything else, right? Because we have to verify all the corner cases. And it seems something went wrong. So if I enlarge this, you will see that we have one pending test. And I will say in advance that this test won't be passed. at the current implementation. In order to understand why it won't be passed, we have to go inside this test and carefully read what it says. And if we read this small description, we will see that it says, for a very long publisher, in case we request integer max value and then request long max value, our publisher should behave normally. So did you get this corner case? Let me switch back to the publisher implementation and write this down. So in case n equal to integer max value and then n equal to long max value, we have this long max value plus integer max value. And who knows what is the answer to this simple exercise of adding long max value plus integer max value?
Use Groovy.
Use Groovy, of course. We can probably write something in Groovy, but let's stick to the Java for this time. So who knows what is the answer?
You should get negative value.
Right. If we let me show you this simple case. I'm going to run my terminal and show you this exercise, if my computer allows me to do that, of course, because it becomes crazy. I don't know what is going on there. So for that purpose, I'm going to run a JShell, which is terminal tool, in order to run Java from the command line. Come on. And if I'm going to write this long max value plus integer max value, I will get a negative result, because the long max value will overflow to the negative one and it will break the whole logic. And unfortunately, this get and add doesn't prevent us or save us from this corner case. So if we look inside this and save, we will see that this is plain read of volatile and then plain sum of both values. This is something not good. So any idea how we can solve that?
We'll try to check it with some log with control and can repeat in case of problems with negative value. To check if we have overflow.
Something near the correct answer. Probably, let me simply answer this question. Probably the simplest solution is to write the same and identical code by ourselves, right? Yeah, in general, this is like almost the correct answer. Please take it. So the simplest solution for us, instead of creating some crazy verification around this get and add, like built-in get and add, we have to provide the same logic by ourselves. And instead of using this get and add, because I'm pretty sure there will be some corner cases in case of which we will shoot in our foot again, we have to simply write the same compare and add loop within get and add by hand. And instead of simply doing this sum here, we will do some smart sum, which check, okay, if our sum gets some negative result in the end, it means that we got overflow. In order to avoid overflow, we have to just put long max value because this is the upper level for long, and that's it. And in this way we can prevent this overflowing. On the other hand, we use the same volatile or atomic compare and set operations on the atomic long, which allows us and which ensure us that everything will be fine with our data exchanging or value exchanging. Is it clear right now what is going on? So the simplest explanation for this, we implemented the same logic with inside get and add atomic long or unsafe, but by our hand. So this pattern calls compare and set loop, which allows us to atomically increment or do some mass operations and atomically set this value back to the memory. And now, if we run all these tests, we will see that everything is fine, which is good. Any questions so far? Is it clear what is going on there? A little bit hard for you? Yeah. Right? So let's back to our slides. And let's do some sum up. First of all, what we saw during this coding session is some usage of atomic primitives, which allows us to provide some efficient, non-blocking memory access. Then we improved our work in progress by infinite loop, which allows us to prevent this racing on the request field and avoid dead code or something like that, or hang code. Finally, we implemented over-implementation of get and add in order to provide or prevent the long max value or long overflow and keep hand on all mass operations that's going within our publisher implementation. To summarize, again, we provided a working implementation of the code for multi-threading environment. Current solution is much complicated. I guess you agree with that, because now we are using, along with this reactive streams ruling, we use a lot of atomic primitives and so forth and so on, and complex multi-threading and concurrent patterns, which complicates our solution a lot. But this is not the end. We have to optimize our solution, and we have to push the performance of publisher to its maximum, because it's really important. Because if we write some slow code, we won't get any benefits from reactive libraries, right? We have to have it really optimized and really performant. So in order to start optimizing something, we have to understand what kind of optimization we can do. What do you think? What we can optimize here? Any idea? First of all, we can optimize some field access. This is one of the options. We have some redundant atomic long field or atomic in field. We have some redundant number of atomic operation in general, so we can reduce the number of atomic operation in our implementation probably. We can reduce the number of produced object, because as more object we produce to garbage collector, the more time it spends on garbaging all this shit that we produce, right? And this is execution time, and this impacts performance as well. Another point which is a little bit tricky and not clear is some execution optimization. Maybe you heard about some CPU optimization like fast pass, slow pass, and so forth and so on. We can implement something similar in our code. And in order to implement this fast pass, slow pass, we can follow some additional rule from the specification. And specification says that if subscriber requested long max value, then we can simply push data without any checking. Because if we go back to the specification and look at the ruling, we will see, let me show you this rule. the sending long max value elements to our subscriber from the publisher can take something like 300 years. And I'm pretty sure your production doesn't live that much without the restarts. So this case is probably a specific case which allows us to simply push data without any verification, and in that way simplifies our code as well. So let's start doing our optimization then, right? But who knows what should be done first before any optimizations? Any ideas?
Measurements.
Right. We have to measure that. Sorry. I will send you another one. Shit.
Just keep him coming.
So we have to write some measurements. We have to make sure that in case we do some improvements, these improvements worth the code we wrote and the time we spent, right? So we have to measure that our optimization is really performant. This is why we are going to use in this current solution, we are going to use GMH. Have you ever heard about GMH, Java Micro Benchmark? So this is a set of built into Java at the latest, at the Java 12. This is a built-in stuff. This is a test suite for checking the performance of your code. Let me quickly show you how it looks like. So first of all, in order to start using GMH in your test, you have to for Gradle you have to add this GMH plugin to your code. For Maven it's a little bit different solution. Then you have to provide this dependency on required GMH lib. As you can see, this is part of OpenGDK, so we can surely rely on this test suite. And finally, what we have to do there, we have to provide a simple test. So in order to start measuring your performance, you have to add this stack of annotations. You have already had this or got this class in your code base. So simply what you have to do right now, you have to uncomment commented lines of code. And I have already prepared for you the old implementation of, or unoptimized or current implementation of array publisher. So this code written here is absolutely identical. IDEA says that it's duplication of our current solution, which is fine because we will compare apple to apple, right? And now we have to start optimizing something. Any idea what should we do first? Let's just follow the guidance I wrote to you. Let's just try to find some redundant atomic operations at all and atomic fields. What do you think? Which field is redundant, and what could be simplified here? Let's just carefully look at the implementation and figure out what is redundant here. Take some time, enjoy this hardcore. Let me give you some advice. Let's take a look at a few code blocks. Let me collapse this guy. Not this guy, but this guy. I pretended to collapse this guy. Let's collapse this guy. And let's define a few places in the code. This part could be accessed by any thread, right? So this part is concurrent.
So index is accessed in a safe way.
Yeah, let me yeah. This is actually this is the correct answer. Then we have this compare and get and add implementation, which pretended to be thread safe in multi-threading environment. And then we have this work in progress verification, which means that only one worker can bypass this check, right? Which means that this part of the code will be executed sequentially, but only one thread. And if we're going to look closer, we will see that only one field is used only within this code block, and this field is index, which means that index can be simplified. We don't need atomic here. And even more, the Java memory model says that if there is a volatile write, which is write to requested field here, if there is a volatile write, then all changes happened before this write will be observed or will be available for the reader once it reads that field. So it means that once we wrote index before this volatile operation, the next read from this volatile read from this field flash any actual information to specific thread, and this specific thread will observe the actual information about index. So what we can do, we can simply make index non-volatile, just a primitive field, and in that way win a huge performance improvement. In order to make sure that we got a really high performance improvement, let's first fix up some code issues. Some code issues here. And in order to understand that everything is fine, let's run benchmarks.
Shouldn't we have index plus plus?
Yeah, we need to increment it.
Right, thank you. I missed that. Thank you. I have to give you two. I'm pretty sure that my computer will show really slow results because for some weirdness my kernel doing some I don't know work. So please run the same benchmarks on your computer. In order to run benchmarks, you just have to run this main method, and that's it. In the meanwhile, let me try to close another things like browser.
Maybe the recording tool.
Could be, but I don't know. I haven't had this experience before this time. So probably one of the options is to restart the computer, but I don't think you want to wait for that. So simply just run the same benchmarks from your computer. It will take a few, like maybe less than 30 seconds or something like that. This is really raw. Benchmark. You definitely have in real benchmarks. You definitely have to increase the number of iterations and the time spent within each iteration. This is just a demo case where I show that anything works. Is no class defined exception. So let's just simply rerun it, rebuild it, and restart it. No, the same shit. Yeah, in order to avoid time spending, I'm just going to show you
from the radio.
Could be. It doesn't matter. Let me simply show you the benchmarks I made a couple of times before, and I recorded them for you. So you will just see. You will be able to run the same on your computer. first of all, and on the second, on the other hand, I will just show you the results. The first results from this plain optimization, and all these results are shown here. You can open your this section in your on the website, and average performance results or performance measurements done on my computer with GDK11 will be about that. As you can see here is unoptimized version, and unoptimized version is about 63 something. Come on, where is that? Yeah, here is it. What's radian, concurrence racing? Yeah, here we go. Come on. Not. Sorry, I'm really sorry for that. Why it happens? I'll just close it. Yes. And the numbers is about that. Do you see it? Should I enlarge it a little bit more? As you can see, the difference is about 30% in performance. So this is before this optimization, before we removed this redundant atomic integer on the index field, and this is after. You should run these tests on your computer. You should increase the number of iterations, but you will see something about this, and you will see something about 30 performance growth in this implementation. All right? Does it make sense to optimize such thing? Okay, so let's move forward, and let's do the next series of optimizations. The next step is to try to avoid redundant atomic reads and writes. Try to make some reads and writes in bulk. And we have to probably make some bulk access to variables, let's name it, or make some access to variables not from the class or fields, but from local stack. Just for your information, access to local field is about 1 or 2 or maybe 4 for some machines or some kernels. You know how to explain that, or CPUs. 1 or 2 or 4 operations or instruction less for CPU than access to fields. So access to stack variables is much less CPU intensive, for example, than access to fields. And moving some fields to local stack can reduce or can win a few CPU instructions for us. Is it clear? Okay, so let's try to analyze what we can do about that. First of all, it's absolutely clear that we can move array lengths out of this iteration, because this is a constant. This is a static value I would name for this subscription, right? So we can replace it with a static field and declare only once per iteration, right? What else? What else we can optimize there? Probably we can move this index out of this access, or we can avoid this right into this index field here. First of all, yeah, before any optimizations, I forgot to mention we have to copy current solution. We have to copy it in order to ensure that we got some improvements by doing that. So let's copy that to unoptimized array publisher. Please do the same on your computer. What do I copy it? Okay, I got it. So yeah, we can just replace this guy here. And now we can apply all this mentioned optimizations related to field access. So instead of reading and writing to index field, we can do that only one time at the very beginning. And then use this if for all these iterations and increments and write it back only once at the very end. So we can do that, or we can flush the index after all this while looping, right? And reduce the number of access to the fields in this way. What else can we do? What do you think about reading from the requested field on every iteration? Do we need that? Any idea? Let's try to analyze the code again. So here we got n, right? Here we got n. Then we bypassed with the same n this verification, which means that we the only single worker at the current moment in time, which means that before requested was 0, which means that now requested equals to 0 to n, right? So we have n equal to requested. So probably if we start doing this iteration, we can replace it with n because we assume that this is the same value. And now, instead of updating this or creating this local variable, we can update n, and in that way avoid using atomic read on every iteration. Does it make sense? Cool. Let's do a couple of latest optimizations. What we can do else, we can move this access to the array to local variable as well, because we don't need it, because this is a constant variable. And after all, we can run our benchmark again. And this time, let me just avoid running this test again, and this time we will get another few % of growing performance. Depends on the use case, depends on the number of first request size. We will get from 1 to 5% win in performance, which is significant because just a few % of performance win can save you a lot of money. Have you ever heard about this Growl and Twitter story where a few % of optimization saved like a lot of money for them? No. Yeah, this is a real story. There is a guy, Chris Tallinger, which is talking about Growl stuff and Growl optimizations, and he did some optimization within Twitter, which won around maybe from 5 to 10% in performance. But for their scale, for their number of machines, this is a real high number of reduced CPU cycle, and in that way they were able to make more or to handle more requests, and in that way they were able to reduce the number of machines and money spent on the cloud and other stuff, which is significant. So winning in a few percent is a huge win for us. So let's move forward and let's do a few final optimization steps. Let's reduce the number of work for garbage collector. Can we reduce the number of work for garbage collector here? Can we get rid of this atomic object? Because this atomic object is objects, which means that we, in general, on average, creates at least one object on each subscriber. And in case of huge amount of subscriptions for a few elements, it can impact performance a lot, right? So can we get rid of this atomic long or this atomic boolean? Do we need here atomic boolean? First of all, let's try to analyze access to cancelled. We have only one write to cancelled field here, and then we have only read access, right? Do we need atomic long here? Do we need all those CAS operations here? No, probably we don't, right? We can simply use volatile here. Right? Because cancelled can be executed like simultaneously, like a part of request method, and reading and writing to this field should be thread safe. Cancelled. So we can reduce all this atomic operations here. And we can simply write atomically here, and that's it. Does it make sense? Yeah, it should. At least. So then, can we reduce this field? Can we avoid creating an object for every subscription? This is a more complex technique. I'm not sure that you heard about such optimizations, but let me do the following refactoring here. Let me move this subscription to inner class. Let me extract this. Extract. Where is that? Yeah, convert anonymous to inner. Let's call it atomic array subscription. Let's move it to separate inner class. Let's make it static, because for the following optimization we need to make this static inner class. Static. Let me pass here the T array from my publisher, and let me bin this. Let me bin this to some field. Let me replace this atomic long with volatile long, and let me do the following trick in order to show how we can reduce the number of produced objects. There is almost identical atomic long field updater. Have you ever heard about that? This is an additional kind of atomic long wrapper, but this atomic long optimizer, let's call it, allows you to create an instance of this updater just for class instance. So since it's static, it will be created only at the class loading period. And in order to make this or to implement this atomic long field updater, or to make this atomic long field updater working, we have to simply say, okay, this is related to this class, so we have to pass this instance of the class, and we have to specify the offset or the name of the field that will be used by this updater. So simply this is a wrapper around unsafe, hidden inside the GDK, and it allows you to say, okay, I know this field is volatile, so I want to have all these atomic long features, but I don't want to create an additional object because of performance. So I simply specify to this atomic long field updater that under the hood find the offset to this particular field, and we'll do all atomic writes and reads, knowing that this memory offset is for this field. Is it clear? It's a little bit complex, but in general it works like atomic long. And now, in order to request it, in order to make this stuff working, you can replace access to volatile object with plain read from volatile field. We can replace this compare and set operation on using this compare and set atomic long field updater, but here the only difference, we specify the object on which we are going to make a volatile read write and compare and set operation. Finally, we are going to use array from our field. Here we can optimize and use instead of index. Yeah, the same here. And here we can use add and get with the specification of the object. And that's almost all the updates. Of course, we can move the subscriber, where is that? The subscriber to local field, replace all the occurrence here. Let's do that this way, doesn't matter. We moved this to separate field. Let's pull it down a little bit and keep it here. And here subscriber. And by doing this optimization, we will win another couple of percentage or percent in performance, and this time the difference is about 5% in performance, which is significant. And this verification, this benchmark were run with additional case in order to check that we really reduce the number of produced objects for some short streams. For example, we create here a stream with only 10 elements, and the execution of such test will take place of like a lot of number of times. So we create a lot of subscriptions, and by reducing the number of produced objects, we can win up to 5% in performance, which is again really significant. Finally, the final optimization, I'm just quickly switch the commit to this point. The final optimization is optimization in execution path, and it means that, as specification says, if we have or if we got n equal to ln max value, we can just simply push data without any additional verification, decrements of volatile field, and so forth and so on. And in that way, win another few percentage. And this optimization can save us or can improve performance in about from 7 to 25%, which is a lot. because in real production, from my experience, there are a lot of cases when we simply say, okay, give me all of you have, and we request long max value, and for such cases we need such optimization because we don't want to have this hard computation on volatile fields, right? Okay, so we have another hour for playing. Do you want some break, some 5 minutes of break? Let's do that. Let me restart my computer because I'm going mad with that speed of my UI. And at the same time, you will be able to take some coffee. So let's do 5 minutes break and back to our exercises. If you have any questions, please come and ask them. And let's do some summary. Delete this open window. Yeah, it's quite loud out here. Cool. So let's back to the presentation. First of all, let's do some final summary of what we did during the, or what we have been doing during the last 2 hours. First of all, let's sum up first part. Do always Java micro benchmark because it's important if you want to achieve some real performance improvements and understand whether your hacks and improvements works or not. Store everything in the stack because access to the stack can reduce a few CPU instructions and in that way produce better performance for your code. Learn specification because in that case specification says that you can optimize or push your performance to maximum by providing some fast pass, and of course remember about reduced number of objects to garbage collector. Finally, to sum up, this is successful optimization because we, in general, starting from the first point and finishing by the final implementation. If we measure the first point and the last point, we will see about 2 times better performance. Our code is about Reactor code. Let me show you. Let me first of all convince you that our implementation is identical to what we have in real libraries like RxJava or Project Reactor. So here we have our array publisher, and now I'm opening Flux array, which is identical, like the same behaviors, but in real library. Like here is the pivotal stuff, and this is a real Reactor core publisher. So this is a real library. And now let's compare those implementation side by side. So on the left hand, we have our implementation. On the right hand, we have Flux from Reactor 3, from Project Reactor, from Pivotal Reactor. You can call it whatever you want. So in general, we have almost identical code. Like first, this is subscription. We have the similar subscription. There is a few optimization, but it doesn't matter. There is the same logic in passing array subscription to our subscriber. This is the first step. Then let's compare implementation of the subscription because this is the most interesting. In general, we have identical code. Let me rearrange it a little bit. So here we have our subscriber. Here we have the same in Project Reactor. The same array, the same index here. The same volatile cancelled. Let me rearrange it again. And the same volatile boolean cancelled in Project Reactor. The same technique in Project Reactor with the usage of atomic long field updater. There is some difference between RX Java. RX Java don't use this atomic long field updater because of some Java 6 requirements. And instead of using static field like this technique, it uses a little bit different. It extends atomic long, and in that way reduce the number of produced objects. So extending from atomic long is also one of the possible solutions in order to avoid producing +1 object in your environment. Since we use Java 8 and higher, we can use atomic long field update. Then let's take a look at the implementation of requested, because this is the most important part. This is the main business logic. Not like that. Let's hold up some piece of code and let's compare. First of all, if we take a look inside validate method, we will see that there is identical validation on n less than 0. But this part is hidden behind additional utils, so we can do absolutely similar, but in our implementation this everything, like all this code inside one place. So this is the only difference between Reactor and us, but in general the same verification as in Reactor. Then the same utility around custom implementation of add and get or get and add loop as here. The same verification whether our sum isn't overflowed as we have here. So we have absolutely identical code. Like here we check our date, our m for the same, and if we go back, not here but here, we will see absolutely identical loop, but the only difference, they use for and we use do while, because there is nothing for difference for compiler and for CPU instructions. For the CPU instructions, this is just the style of the code. And from the other perspectives, they use the same technique with compare and set, and that's it. Move forward. We have the same fast pass, slow pass optimization in Reactor, and we have the same fast pass, slow pass optimization in our code. Let's take a look at slow pass first. Here we have the same usage of all fields within the stack. We have the same optimization of index. Moving to stack, we have the same send, but in our case, send is readable variable. In their case, it's a little bit ugly. This is all about Reactor's RX Java code. The variable's name is a little bit inconvenient compared to Spread and other source code from Pivotal. Thus, it's a little bit tricky to read all this code. So knowing this implementation that we just provided, just custom implementation of array publisher, you will be able to read all this code, because in general we can link this stuff with their stuff, right? We can a little bit rearrange this and that, and we end up with almost identical solution. But our code is a little bit readable, their code is less readable than our. Like this, one-to-one. Now, the only difference between our loop and their loop in the style. We have while true, they have infinite for loop. The same cancellation verification, the same null pointer verification as in our case, the same data sending as in on next. But we have this send an e increment within the for loop. They have that in while loop. Just a switching code style. Then the same completion verification and almost the same technique for decrementing and incrementing data. So I haven't shown you this optimization, but this is kind of double check for current state of requested. So instead of doing atomic write, which is kind of expensive operation from the CPU perspective, from the CPU operations perspective, we can proactively read the requested field and check if n doesn't equal to number we produce to our subscriber, then we don't have even try to write to requested field, and we can continue iterating with the same state but with updated n. And this is another optimization which can save us a few portion of percent in performance. And the fast pass is absolutely the same as here. Plain looping through all the data without any additional verification, and that's it. And in that way we achieve absolutely identical code as in real project. First of all, it's clear that I'm one of the contributors to Project Reactor, so I can just rewrite the same code for you, but the main intent of these exercises is to not only convince you with why this code works like that, but help you simplify your life when it comes to debugging of this code. Because when you start debugging the reactive code, you will enter this real, for example, internal stuff, and you will have to understand where to put the breakpoint, why it's written in this way, why we have too much volatile fields, why this not volatile. And now, attending this presentation, you will be able to recognize all these patterns used. You will be able to find the place where to put, and the place where to put the breakpoint is definitely within this work in progress loop, right? So you currently know where to put it. Now you know that all data sending is done within the request method. So you know that once you request something, you can end up within this piece of code. And now you know how it behaves in general, right? All right, let's back to final slides. Let's skip it. Let's remind some patterns we used during the workout of that. First one is work in progress, in order to prevent recursive access to the same from next method to request and so forth and so on. The next part, in order to improve our code and in order to avoid some racing condition, we can use infinite loop in the way of while true, and additional verification whether we send all the data and we don't have anything else to send. Then we can use some fast slow pass in order to improve the performance, and this is used with combination of long max value, because long max value indicates that this is just push only stream. And finally, we can use atomic XXX, because it could be integer, it could be long, and it could be, I don't remember which atomic reference field updaters, in order to reduce the number of provided object to garbage collector, right? So the summary of the first part. Don't afraid it. Just read the spec and do it step by step, and you will find all the logical pieces in the real implementations. Everything is done for performance, because performance is the most important part in reactive streams. We will come back later to the performance of real piece of code, but everything you saw in this presentation is done for performance. TCK can simplify verification of your code, and as one of the amazing person, Venkat Subramanian, says, wash your hand after becoming a god, which is, this is a Russian word, but in general it means wash your hand after shitty code. Alright, this is the first part, but this is not the last one. We have to dig deeper inside Reactive, and now we are going to finalize our knowledge about Reactive Libraries by building real Reactive DSL and functional library around what we did in the first part. Alright, any questions? So, in order to not just making and writing the library, we are going to solve some real or near the real world case by implementing the order processing. So let's try to analyze what can be included in the order processing. First of all, the order processing, just imagine it could be a web page, it could be, I don't know, processing pipeline, it could be cloud functions, whatever. But in general, when it comes to order processing, it comes to receiving some order with some information about products. So at the very beginning of our pipeline, we receive a list of products, right? Then, since, for example, Amazon or big web stores can work with different currencies, the different dealers and the different markets can sell their product in real currency, right? So we can select, for example, on the web page that we want to see all the products in euros, but in reality, the price of this product is set in dollars or in hryvnias, Ukrainian, or whatever other currency or world currency. So as the second step, we have to do some pre-processing of our order list, and we have to find the real price in terms of, we have to convert the dollar price to euro price, for example. And this is the second step in our pipeline. The third step, we have to do some sum up of all the costs in order to produce the answer to our customer. And finally, we have to apply some discount because we love our customers, right? We love when someone buys our product, and that's why we always prepare some discount for our for all products, and we, as a final step, can apply some discount on general sum for all products. Is it near the real production case? So in case it is, we are going to move forward, and we are going to look how it could be implemented in imperative way, right? So let's take a look at that, and let's take a look at our project. For this exercise, we have to switch our branch to another one. We have to move to part 2. There is a branch origin. Do you see it? There is a branch origin part 2 by steps commit. So just switch to that branch. And open commits logs again, because there is a full implementation there. And check out the part 2 commit. You will see this history, but you have to check out to that point. Any problems so far? Is it clear? Cool. Then let's move forward, and let's take a look at our updated application. First of all, we got a few more classes in our code base. First of all, this is the first the class with the name application, which has one main method, which creates the two services, like currency service, which is in memory currency converter. Nothing special there. And the second one is business logic processor or orders processing, right? This is the part of the code which is responsible for accepting our order and return total order amount with the discount. And here we have some imperative data processing. So we call for currency conversion, we do some currency conversion here in imperative way. Then we do another, we do some reduction to one object of all products. So product can, or order can have a few products inside. So we are going to reduce everything to one total amount. Then we apply a discount on this total amount, and then we return this object back to our user. So this code reflects what I described a couple of minutes ago. This is our pipeline written in imperative way. It's real common, but what we want to have, we want to achieve some more reactive stuff here. We want to see how we can improve that with reactive programming, and first of all, because this can be a distributed code. This can live in real network, and we can asynchronously accept incoming data, and we don't want to process everything in blocking synchronous way, because this can impact performance as well. And asynchronous and blocking and reactive is about performance improvement and better CPU utilization and so forth and so on. So we want to have all these benefits. And for that purpose, we have to build some additional operators to our library. Right? Is it clear? Okay, then let's switch back to our presentation and let's talk about reactive prerequisites. First of all, we have to have a few operators. Such operators could be map, the simplest one, filter, take, and if we got some time to play around publish on, I will show you that everything we learned in the previous part is applicable to even complex operator like publish on. So this is the first part, is simple one, and if we got some time, we will work on publish on as well. In order to understand and in order to start writing real operators, we have to understand the life cycle of reactive streams in general. That's why I want to spend a couple of minutes on that part. So let's talk about life cycle. When we talk about life cycle, it means that there is a few stages in reactive streams. The first stage and the first step that we ever do, we create a publisher, right? We create an instance of publisher, of our producer, because we want to achieve something in reactive way. This is the first stage, and this stage is called assembling, or assemble time, or assemble part of life cycle. The second step in the life cycle is subscribing. When we call the subscribe method, and at that point in time, we provide a subscriber which is interested in achieving or receiving data. This subscriber, I would say, flowing up or I don't know how to explain that, but it migrates. Our publisher get an access to this subscriber, and as the first step, it sends on subscribe or it call on subscribe method and sends a subscription to our subscriber, right? This is the first step, and this part of the life cycle is called subscription time. When we provide the subscriber is coming to RA publisher exchange or send it a subscription, and in that way there is an exchange of information or access to internals of each other. And the last part of all this execution is data sending. And it starts when we request first few elements. So we say, okay, give me 5 elements, and our publisher starts sending elements to us. And finally, it can end up with incomplete, and we terminate our life cycle at that point. And this part of the life cycle is called as runtime, because at that point in time we exchange the real signals like request on next, and complete, and so forth and so on. And this is runtime phase in reactive streams. Is it clear? So now, counting all this information, let's think how we can implement a map operator. Yeah, let's recap. Assembling is creation of a publisher, subscription is sending a subscriber to publisher, and publisher sends a subscription to subscriber. And runtime is exchanging of the rest of the signals. So now let's think how we can write the same code, the same array publisher, but with two maps operator. Any idea? Let's think when those transformations applies and what is mapping. In general, mapping is transformation or converting A to B, right? So in general, when we think about such code, we see some lambda, pass it to map operator, and this lambda is executed on every incoming element in order to convert this element to another one, right? So if we think about that, it means that everything happens at runtime period, right? So basically when we subscribe, array publisher starts sending data. Every element converts on every stage, and finally got to subscriber. That's what is going on. So what stage is that? What life cycle part is related to this transformation? We got assembling, we got subscription, which is call of subscriber and non-subscribe method, and then we got a runtime, which is calling of on next method. So what execution period is that? Runtime, right? So this is runtime. So all we have to do in general in order to implement mapping, we have to provide a few subscribers and every subscriber will do a transformation once it receives a new object on it. So in general, in order to implement this in code, we have to apply some additional pattern like decoration in order to decorate one subscriber into another and into another in order to create a chain of on next execution with some additional logic. So let's try to do that, but what about the rest of the phases? Do we need them for such operators? Can we just combine a few subscribers? Just imagine a real code. For example, let me quickly switch to the idea. Let's imagine we accept a publisher here, and as a step of transformation, we usually returns publisher as the output step, right? So now, just try to think how we can apply just a plain subscriber here. Do we have an access to real subscriber at that point in time? Because we have just incoming stream and just outgoing stream, and we want to apply some intermediate operators. I guess it's impossible without having an additional wrapper, right? So probably one of the solutions should be providing some decoration around publishers at assembling time. And instead of just decorating subscribers, we can decorate publishers, which can then decorate as subscribers in that way. And after all, we will be able to bypass all data through all elements of the pipeline, right? So now we have to at least implement two parts of the, we have to decorate two elements in our reactive streams. But is that enough? Let's just try to do that. Let's just try to do that. First of all, let's just revert all of those changes. And now let's try to create an instance of map publisher there. As I said, all we have to do is decorating. So we have to extend or implement publisher interface. We have to implement publisher interface. Since it should be generic enough, we can just simply say, okay, we want to have generic type T to any element, but since map does a conversion, we have to specify a second generic element because we are doing some conversion. Of course, we have to have some mapper here, so it should be a function, then accept T and return error, and this should be a mapping function. And of course, since this is about decoration, we have to have a publisher of type T. And right, we have to return, we have to be a publisher of type error. So this is the source. Now we can implement one method. We can add constructor params. And now we have to decorate our subscriber. So as I said, at that point in time we receive the subscriber, so we have to add or to adjust some additional logic. So let's just create a class for that. Let's just create an inner class map. Let's call it map operator. Let's make it implementing the subscriber interface. And let's just implement those methods. It's clear in order to provide decoration at that stage, we have to have the actual downstream, so we have to get this actual subscriber to whom we have to send our transformer data. And it's clear that we have to get this subscriber here. Also, we need our mapping function from there. And after all, we have to pin this to field. And do some logic propagation. So first of all, we have just decorate this method and send, again set, and say, okay, we just propagate subscription downstream. At that point in time, we have to do the same. We have to say, okay, just actual on next. But before doing any data sending, we have to convert this element to another one to some result. So we have to apply our mapper. Say, okay, mapping. We have to give him an element and receive the result. And then we can send this result downstream. Finally, we can do absolutely the same for the rest of all the operations. And delegate all those calls to our downstream. Final step in our exercise is we have to simply, we have a source, no, we don't have to return anything. We have a source, so we have just do this decoration on all the levels. And at that point in time, we have just to wrap incoming subscriber to the map one and provide this additional mapping to it. And in that way we have implemented mapping logic in one operator. Any questions so far? Is it simple enough? Just one pointer in order to decorate two elements in reactive streams and provide some additional business logic, right? This is really simple. So let's back to slides. Let's cover some corner cases. So what we are going to do in general, we are doing some chain of responsibility with decoration pattern, and in general it seems like we got a subscriber which is wrapped in another subscriber which is wrapped in another subscriber. That's it. The same we have for our publishers. at the assembling stage, we have to pass one publisher into another, into another, into another, in order to get this decoration chaining. Finally, let's try to talk about some corner cases. By the time we just consider it a success plus, right? We got like a circle and we converted it to the square and so forth and so on, and square to triangle. But just imagine, what if the user is really an evil user and he decide to convert circle to null square, right? It's possible because the user isn't mandated to follow reactive streams. This is just an API. This is not about internals rules. So our implementation should protect us and protect user from all these corner cases when he can convert or he can convert any element to null. In that case, we have to, once we get a null, we have to throw the null pointer exception in the right way, right? So we don't have to just propagate null because it's incorrect. We have to behave in the right into the corresponding to specification way, and instead of sending data downstream, we can say, okay, this is null, this is something incorrect, so we have to unsubscribe from upstream, we have to cancel the subscription because this is the only way, and we have to say, okay, subscriber, something went wrong, here is the error. Now let's think, can we do that in the current implementation? Can we cancel the subscription first of all? Do we have access to subscription at the moment? No, we don't, because we don't do a full decoration. We did a decoration of the subscriber, we did a decoration of the publisher, but we didn't do a decoration of subscription. So let's do a decoration of subscription as well, because it's important. And what we have to do here, we have to store subscription in the local field once we receive it. And then, instead of propagating this subscription downstream because we don't have, without proper decoration, we lose the access to this subscription, we have to provide another implementation of subscription and delegates all the calls to the real subscription through the chain. Finally, in case we got some illegal element, we can do something like that. So we can do some verification null and say, okay, if it's null, just throw an exception and put it within some try catch in order to collect some stack trace, because it's important when it comes to debugging. Catch this exception. And now, since we have an access to subscription, we can say, okay, cancel. Goodbye, my dear friend. We don't need any data anymore. Anymore. And now we have to send, okay, we have to say on error and send this error to our subscriber in order to notify him about this exception. Final.
So we have a club?
I'm calling internal method which has this by propagation. I'm calling to myself, so it's fine. But there is one corner case which is less visible here, and this corner case related to the fact that cancellation is eventual or can be asynchronous, which means that even though we cancel the subscription here, we can still receive some elements or some signals. And specification sends that subscriber should be ready to receive a new element or a new on next on or an error on incomplete signals after cancellation, because we can't guarantee immediate cancellation. Thus, we have to provide an additional flag here. This is one corner case, and we have to add this flag boolean done, which means that we're done with our execution. And we have to protect our data send it with this flag. So if it's done, then it's done. We don't need to send anything anymore. So let's just copy paste it and put it to every column. And now this is almost the final implementation. Since you remember that we don't have to produce another few objects to garbage collector, we can optimize it and we can implement both interfaces at the same time. So the subscription, that our operator could be a subscriber and a subscription at the same time. And instead of propagating all this a new anonymous object to downstream, we can propagate ourselves. And we can say, okay, let's just implement those methods here. And this is the finest implementation of map operator. Again, let's compare it quickly with Flux map, and you will see the same. This is a combination, like this is an additional wrapper for internals, but in general, this is subscriber and subscription at the same time. So both interfaces in one place. The same additional validation because of some circumstances, but we are avoiding this. And here we have the same down verification. But since Reactor is a little bit smarter, there is a lot of additional operators for catch and drop it elements and so forth and so on, and we are not going to do that. But in general, the logic is the same. Verification on null. If it's throws, then we are done. And the logic of cancellation and sending on error is here. So we got this subscription and cancel it, just hidden inside utility classes. And that's it. The same logic is in on error on display. So we are about the same implementation with Reactor again. The exercise for you is to implement tests for this, like TCK test for this map operator. We are going to avoid that, and we're just going to implement the rest of the operators for filter and for take. Since now we know the patterns, we can simply copy paste map implementation and call it filter publisher. And instead of predicate, function replaced with predicate, and so forth and so on. I'm just simply go to and switch to particular commit in order to save our time and show you the identical implementation of filter publisher. The only difference is this predicate instead of mapper. The same code here is the same decoration. For take operator is a little bit more complex, but in general the same patterns. Now for take, since the intent of take operator is to take a few elements, just a few elements from stream, like in Java streams. Take, for example, 10 elements, we have to know about how many elements we have to get, and since we know we have to compare whether we reach the limit, let's name it, we have to count the produced number of elements. This is the only difference between previous implementations. And that's it. Once we reach the limit, we cancel the subscription and say we are done. The end is similar. So let's back to our slides and let's do a small sum up. In general, null is unacceptable, so we have to protect from these cases, and we must throw NPA in the correct way. We have to cancel upstreams when it comes to this corner case, and in order to do that, we have to provide a decoration of everything, and we have to stop processing data in that way. So we have to remember that once we cancel upstream, we have to say, okay, we have to, as quickly as possible, mark our state as done and don't accept any data from the upstream. Yeah, we did that, and we did that. So we got really straightforward code. Decoration saves the world. That's what we can say about the previous exercises. Now let's back to our order processing and let's try to implement that in the reactive way, right? That was our main intent. So let's do and let's revise our order processing service, and now let's make it returning reactive types, right? Because we want to achieve that. So we wanted to have a publisher as incoming type, and we wanted to have a publisher as return type, right? So now let's apply those transformations. Now it's clear that here all the operations is mappings. So we have to provide here a decoration using map operator. Since we don't have any API so far, we are going to use this decoration, and we decorate everything by hand. We're going to use this. We're going to use method reference in order to provide reference to this transformation, since our publisher receives order request, and we need transformation hidden here. So this is transformation of order request to another state. So we are doing this like this. Since the result of this transformation should be transformed in another state, we have to decorate this map into another map. It's hanging again. So we have to do something like that. We have to provide this. We have to remove that, and we have to now do this transformation here. Then we have to wrap this mapping into another mapping again, because we need to add another transformation of the data. So we have to create another mapper, and so forth and so on, until we do all this required mappings. And yeah, let's quickly paste this guy. And provide final applying of application of discount, and this will be the final step in our transformation world. Does someone see this pattern, this picture? This looks like a pyramid of doom, right?
Yeah.
Okay, we will be back to that, and we will revise that. But let's just return this guy, because we are running out of time, and check whether it works or not. Okay, for that purpose, I'm going to switch to another PR. And show you how it looks like in the final state. So as I said, this is the same decoration, so this is the same pyramid of doom. And now, in order to subscribe to this guy,